Good day. So here in this lecture, we will be discussing buoyancy. But before we discuss this topic, let me just show you an article about an owner of Mitsubishi Expander makes his car float to protect it from flood. So how is this possible that a car that is so heavy was able to float on the flood water? So it makes you think, why do things float? Why some objects float on water and some objects sink on water? So, dyan papasok ngayon ang ating topic, which is about buoyancy. And one principle that we are going to consider here is the Archimedes principle. So, according to Archimedes, any body immersed in a fluid is acted upon by an upward force, which is called the buoyant force, equal to the weight of the displaced fluid. So, this law of hydrostatics applies to submerged bodies and floating bodies. So, what is buoyant force that is being referred to here? So, as mentioned earlier, the buoyant force is that the upward force that is acted upon by the fluid, which is equal to the weight of the displaced fluid. So, we can say that the buoyant force is just the product of the unit weight of the fluid where the object is being immersed to multiplied by the volume displaced. So that volume displaced is just the volume of the body below the liquid surface. So say for example, if we have here a submerged body, so if we are going to determine the vertical forces present between this body and the fluid. So we have here the weight of the object, which is of course going downward, and as mentioned earlier, there is an upward force applied by the fluid on that object where that object is being submerged to. So we have an equivalent buoyant force which is going upward. So to compute that buoyant force, you just have to multiply the unit weight of this fluid by the volume that is displaced, or the volume of the fluid, or the volume of the object that is occupying the fluid. So since this is the liquid surface, so the body is fully submerged on the fluid. So what you are going to determine for the volume is the whole volume of this object right here. So it means that if that body sinks on the fluid, the weight of the object is greater than the buoyant force. So the body will sink if it is heavier and the buoyant force is not enough to lift that object. Okay. So for floating bodies, so if we have again the weight of the object and there is an equivalent upward buoyant force, so the volume required here, or the volume displaced for the buoyant force, is just, if we will just extend a line from this liquid surface, okay, the volume displaced is just this volume right here that is displaced by the object, or the volume that is supposed to be occupied by the liquid surface, but now it is occupied by this object. That's why the liquid pushes it upward by its buoyant force. So this is your volume displaced. Okay. So if the body float, it means that the weight of the object is equals to the buoyant force. Okay, so that's it. Same applies with a balloon where our fluid here is the air. So if the balloon is not floating, it means that it is heavier than the buoyant force. Okay, so usually this type of balloons are just filled with air. Okay, while the other one is a floating balloon where it is filled with helium, which is a lighter gas compared to the atmosphere. Okay, with air. So the buoyant force is greater than the weight of the balloon. So the balloon will just keeps on rising, okay, until it reaches equilibrium, where the buoyant force will equate to its weight. Okay, so let's start solving some problems which involves buoyant force. Okay, problem number one. We have here an iceberg having a specific gravity of 0.917. It is floating on salt water of a specific gravity of 1.03. If the volume of ice above the water surface is 1000 cubic meter, what is the volume of ice? Okay, so usually we think that ice is just made of water, but when water becomes ice, so its specific gravity changes, okay, or its unit weight changes. It becomes lighter than the liquid water. So here in this example, we have here an iceberg which has a specific gravity of 0.917, and we have a seawater of specific gravity of 1.03. What is given here is that the volume that is above the water surface is 1000 cubic meter. So if we are going to shade that area, this is the volume that is above the liquid surface. So let's write first the given. Okay, we have specific gravity of ice 0.917, specific gravity of seawater, that's 1.03, and that's it. We have a volume above the liquid surface, let's say that's VA. Okay, volume above the liquid surface is 1000 cubic meters. So what are the forces present here? So we have the weight of the ice and the buoyant force, which is upward, EF. Okay, so to compute the weight of the ice, if we have a given specific gravity of the ice, we can compute its unit weight to be multiplied by its volume, total volume of the ice. Okay, so the unit weight of the ice is 9.81 kilonewtons per cubic meter, which is the unit weight of water, to be multiplied by the specific gravity of the ice, which is 0.917, multiplied by 1000. Nope, that's total volume. Okay, total volume of the ice. Okay. So total volume is still unknown. So the weight of ice is equals to, okay, 9.81 by 0.917, 8.996. 8.996. This is in kilonewtons per cubic meter still, multiplied by volume. So this is your weight of the ice. Okay, how about the buoyant force? So let me write here the buoyant force. The buoyant force is just the product of the fluid, which is the seawater, unit weight of seawater, by the volume displaced. So our volume displaced here is this one, okay? The volume that is submerged on the water. Okay, so how do we determine the volume displaced? So the volume displaced, if we have a given that is the volume above the the liquid surface, so we just subtract the total volume, okay, let's say V, total volume of the ice, to be subtracted by the volume above the liquid surface. So that's V minus 1000 cubic meters. So that's your volume displaced. Again, total volume of the ice is still unknown, so we just express that as V. And now, computing the buoyant force, we have 9.81, or unit weight of water, multiplied by the specific gravity of seawater, okay, to compute its equivalent unit weight of water, or unit weight of seawater, multiplied by the volume displaced, which is this one, V minus 1000 cubic meters. Okay, this is another equation. We have the weight of ice and the buoyant force. So, by taking the sum of the forces along the vertical, considering downward as the positive, or we can also assume that upward is positive, okay? Taking the sum of the forces along the vertical equals to 0, and assuming that upward is positive, we have here buoyant force, which is positive, minus weight of the ice, or vice versa, negative weight of the ice plus buoyant force, that is equals to 0. Or simply, the buoyant force is just equals to weight of the ice. Okay, so substituting now the computed values earlier. For the buoyant force, let's simplify this first. 9.81 by 1.03. Okay, sorry, 9.81 by 1.03. That's 10.1043. 10.1043 kilonewtons per cubic meter multiplied by V minus 1000 meters. So substituting that here, and this weight of the ice right here, we have a buoyant force which is 10.1043 kilonewtons per cubic meters by V minus 1000 cubic meters is equals to 8.996 kilonewtons per cubic meter multiplied by V. So the only unknown here is the volume of the ice. Okay, so we multiply 10.1043 by V minus 1000. Distribute that, we have V in kilonewtons per cubic meter minus 10.1043 multiplied by 1000, that's 10104.3 kilonewtons equals to, just copy this, 8.996 V kilonewtons per meters. Okay, combine like terms. We transpose this term here on the left hand side of the equation, and this constant right here, this term 10104.3 to the right hand side of the equation. So we have 10.1043 V kilonewtons per cubic meters minus 8.996 V kilonewtons per cubic meters. So this V right here is our variable for total volume of the ice, and this becomes positive 10104.3 kilo. So combining like terms, we can subtract 10.1043 minus 8.996. That's 1.1083 V kilonewtons per cubic meters. That is equals to 10104.3. So dividing both sides by 1.1083 in kilonewtons per cubic meter, 1.1083 kilonewtons per cubic meter, what unit remains is cubic meter. So the volume is equals to 1.1083. Okay, the total volume of the ice is 9,116.936 in cubic meters. Okay, so that's how you solve the volume of the ice if we have a given volume which is above the liquid surface. Okay, just make an equation equating the weight of the ice by its buoyant force. But if there are external forces, you should also include that. Okay, if we have an external force being applied here, okay, when we take the sum of forces along the vertical. Okay, so that's how you solve this problem. Okay, but if you want to if it is required here to compute the buoyant force, we can compute that since we already have the total volume, which is 9116.93936. So if we are going to compute the total buoyant force, we have 10.1043, which is in kilonewtons per cubic meters, multiplied by the total volume, which is 9116.936 cubic meters minus 1000. Okay, so the buoyant force is equals to, I will just directly solve this class just to show you how to compute the buoyant force when we already have the total volume. So of course the volume displaced is just required for the buoyant force, so we have to deduct the 1000, okay, for the volume displaced. So this is your buoyant force, 82,015.956 kilo newtons. So just to verify that we have an equal weight of the ice and the buoyant force, I will just multiply here in this equation 8.996 by V, which is 9116.936. Okay, so we have the same value for the weight of the ice when I try to substitute here on this equation and the buoyant force. Okay, so we move now to the next problem. Problem number 2. A block of wood 0.6 by 0.6 meter and an unknown height in dimension was thrown into the water and floats with 0.18 meter projecting above the water. The same block was thrown into a container of coconut oil having a specific gravity of 0.9 and it floats by 0.14 meter projecting above the surface. Determine the value of the h or the height of the block and the specific gravity of the block and the weight of the block. Okay, so let's solve this. We have the same object, which is a block of wood, thrown on different liquids. So the projecting height from the liquid surface are different. So how do we solve the total depth of this block of wood here? So what are the given? Uh, Given we have a specific gravity of coconut oil. Okay, that's 0.9. Okay, the cross-sectional area of this block of wood. Okay, we have 0.6 by 0.6. So we just simply write that as area, cross-sectional area, which is 0.6 by 0.6. So that's equals to 0.36 square meters. Now, there's no other given. So, in solving this, let's take into consideration first this block of wood that is in water. So, in water, we will just make an equation again, which is the sum of the forces along the vertical, say upward positive, equals to 0. So the forces present here are the weight of the block of wood and the buoyant force. So taking the sum of the forces, we have buoyant force upward subtracted by the weight of the wood equals to 0, or the buoyant force equals to the weight of the wood. So solve this, we can just simply write that the buoyant force is just the product of the unit weight of water by the volume displaced. That is equals to weight of wood, unit weight of wood multiplied by the total volume of the wood. Okay, so based on the dimensions given, if we're going to determine the volume displaced, so it is said there that the projecting distance from the water surface is 0.18. So if we have a total depth of h, so the distance from the liquid surface to the bottom of this block of wood is h minus 0.18. So if we're going to compute this volume displaced right here, which is this volume that is submerged or immersed on the fluid, so we just simply multiply the cross-sectional area, A, by the depth, which is h minus 0.18 meters. So this is your volume right here, okay? This is your volume displaced. So for the wood, weight of the wood, unit weight of wood multiplied by the volume of the wood. So what is the volume of the wood? Just multiply the cross-sectional area by its total depth. So the cross-sectional area is multiplied by the total depth, which is h. So the unit weight of wood is unknown, so there's no given specific gravity of the wooden block. So if we're going to determine the unit weight of the wood, we can just multiply the unit weight of water by the specific gravity of the wood. So this is unit weight of water multiplied by specific gravity of the wood multiplied by A and H. So here's our equation now. So there are common on each side of the equation. So we have common unit weight of water and cross-sectional area. So if we are going to divide both sides by the unit weight of water, it can be cancelled out. Okay, unit weight of water and the cross-sectional area of the wooden. So it can be cancelled out. when we divide both sides. So what remains is H minus 0.18, that is equals to specific gravity of the wood by H. So if we are going to make an equation expressing determining the specific gravity of wood in terms of H, we can say that when we divide both sides by H minus 0.18 over H is equals to specific gravity of the wood, or we can rewrite that as the specific gravity of wood is equals to H minus 0.18 over H. This is your equation 1 right here, because we have two unknown variables, the height of the wooden block and the specific gravity of the wood. So we are going now to consider the wooden block, which is in coconut oil. Okay, when the wooden block is in the coconut oil, we have a projected height from the liquid surface of 0.14. So again, let me just copy this figure right here. Okay, so let's say it's right here. So in coconut oil, we make again an equations taking the sum of the forces along the vertical. So what are the forces present here again? We have the weight of the wooden block and the equivalent buoyant force. So taking the sum of forces along the vertical, upward positive, so we have buoyant force equals to, or buoyant force minus weight of the wood, which is just the same, equals to 0. So the buoyant force is equals to weight of the wood. So buoyant force, just the product of the unit weight of the fluid, unit weight of the coconut oil, multiplied by the volume displaced, equals to unit weight of the wood multiplied by the total volume of the wood. So unit weight of oil, we have a given specific gravity of oil, which is 0.9. So 0.9, we just multiply unit weight of water by specific gravity of oil, which is 0.9, multiplied by the volume displaced. The volume displaced is this volume right here. Okay, so cross-sectional area multiplied by its depth, which is h minus 0.14. So let's say A, h minus 0.14. Okay, equals to unit weight of wood, unit weight of water multiplied by specific gravity of wood, and the volume of the wood, total volume of the wood is cross-sectional area multiplied by the total depth, A multiplied by H. Okay, so we have common values on the left and right side, so we can divide both sides by the unit weight of water and the cross-sectional area, so that it can be cancelled out. Okay, so what remains is 0.9 multiplied by h minus 0.14 is equals to specific gravity of wood times h. Okay, so if we're going to divide both sides by h, we have the specific gravity of wood, which is equals to 0.9 multiplied by h minus 0.14 over h. But here, in this equation, we can now substitute equation 1 from the equation derived from the sum of forces when the wooden block is in water. So we substitute here specific gravity of wood, which is in terms of H, here on this equation right here, which is, let's say this is equation 2. So we substitute specific gravity of wood. Okay, substitute equation 1 here in equation 2. So 0.9 H minus 0.14 is equals to H minus 0.18 over H multiplied by H. So we have 0.9 H minus 0.14 equals to H minus 0.18. Okay, distributive property, we have 0.9 H minus 0.9 by 0.14. That's 0.126 equals to H minus 0.8. So combining like terms, we have here 0.9H minus H equals to negative 0.18. This negative here becomes positive 0.126. So we have negative 0.1H is equals to negative 0.18 plus 0.126 negative 0.054. Okay, so dividing both sides by negative 0.1, negative 0.1, we have an H which is equals to positive 0.54. Okay, 0.54. That is in meters because our units used here are in meters. So I didn't write maybe, but they are in meters. 0.14. Okay, so that is 0.54 meters. That's your total depth of the wooden block. Okay, so that's the answer for letter A, the value of H. For letter B, the specific gravity of the wooden block, we can now compute that since we have already H. So we can use this equation 1 here for letter B. So the specific gravity of the wood is H minus 0.18 over H. So we have 0.54 meters minus 0.18 meters to be divided by 0.54 meters. That's your specific gravity of the wooden block. Okay. Specific gravity of the wood is 0.667. So it is lighter than water. It's less than 1. So it will really float. Okay, this is your specific gravity of the wood. How about the weight of the block? For the weight of the block, wooden block, letter C, for the total weight, we just simply multiply the unit weight of the wood by the volume, total volume. So determine the unit weight of the wood, multiply unit weight of water by specific gravity of the wooden block and its total volume. Okay, volume of the wood. So we have 9.81 kilonewtons per cubic meters multiplied by specific gravity, which is 0.667, multiplied by volume of the wood. So the volume, we have a cross-sectional area multiplied by H. So 9.81 kilonewtons per cubic meter by 0.667. Cross-sectional area is 0.36 square meter. So 0.36 square meter multiplied by H. Total H is 0.54 meters. Okay, now solve this. what unit remains is in kilonewtons by 0.667, 0.36, 0.54. So the weight of the wood in kilonewtons is 1.272 kilonewtons. So this is your answer on question letter C. Okay, so that's how you solve this problem, class. Next problem. The block shown in the figure weighing 155.74 kilonewtons. Find the value of each. So here we have a block that is floating on two layers of liquid. We have oil and water. The oil has a depth of 0.91 meters, and we are required to determine the depth to which that block is submerged in the water. So this is unknown here. So what are the forces present here on this body? We have the weight of the block, which is 155.74 kilonewtons, and we have a buoyant force, which is, since this block here is submerged in two layers of liquid, we have two buoyant forces. The buoyant force due to the oil, applied by the oil, and the upward force, or the buoyant force applied by the water. So taking the summation of forces along the vertical equals to 0, assuming upward is positive, we have buoyant force 1 plus buoyant force 2 is subtracted by the weight of the block equals to 0. Okay, so let's find first the values for the buoyant forces. For the buoyant force 1, we have the unit weight of the fluid, which is the oil, multiplied by the volume displaced. So what is the volume displaced here? This one. Okay, this layer here. So the unit weight of oil is just the product of unit weight of water, 9.81 kilonewtons per cubic meter, multiplied by the specific gravity of oil, and the volume displaced. So the volume displaced is just the product of this. We have a given area, which is 3.66 by 3.66 meters. So we just multiply it by the depth, which is 0.91. So 3.66 meters, 3.66 meters by 0.91 meters. Okay, so the buoyant force is equals to 95.667 kilonewtons. That's for the buoyant force 1. For the second buoyant force, due to water, we have unit weight of water multiplied by the volume displaced again. Unit weight of water, 9.81 kilonewtons per cubic meter. Volume displaced, we have an area multiplied by the depth, h. So that's 3.66 meters by 3.66 meters multiplied by h. So 9.81 by 3.66, that's 131.411 kilonewtons per meter. So cancel that. We have h multiplied by h. So BF2, we have a variable h, which is required. So we can now take the sum of forces, since we have already a given weight of the block. Okay, we can just substitute that. So from this, substituting the values, we have buoyant force 1, which is 95.667 kilonewtons plus 131.411 kilonewtons per meter H minus 155.74 kilonewtons equals to 0. Okay, what is required is H. So we can now solve H. So let's move these two terms here on the right hand side of the equation. So what remains is 131.411 kilonewtons per meter multiplied by H equals to uh, this becomes positive 155.74 kilonewtons. This one becomes negative 95.667. Okay, so let's rewrite that again. Combining like terms, we have 155.74 minus 95.667. 60.073 kilonewtons. Dividing both sides by 131.411 kilonewtons per meter. Okay, so we cancel out. What unit remains is in meter. So the H therefore is equals to 0.457. That's in meters. Okay, so this is the answer. That's the height H. So, last problem. A hollow cylinder 1 meter in diameter and 2 meter high weighs 3,825 newtons. How many kilonewtons of lead weighing 110 kilonewtons per cubic meter must be fastened to the outside bottom of the cylinder to make it float with 1.2 meters submerged in water? So for letter A, this is what it looks like. So we have a hollow cylinder with a height of 2 meters and 1 meter diameter. So what must be the weight of the lead to be attached the bottom of that cylinder in order for it to float at 1.2 meters below the surface, water surface? Okay, so for letter B, how many kilonewtons of lead if it is placed inside the cylinder? So if we place the lead inside the cylinder, and in order for it to float at 1.2 meters submerged in water, what must be the weight of lead to be placed inside the cylinder? Okay, so solve this. What are the given first? We have a given diameter 1 meter. Okay, height, that's 2 meter. That's for the dimension of the cylinder. Its weight is 3,825 newtons. So we convert that to kilonewtons. That's 3.825 kilonewtons. Okay, that's the weight. So next we have here unit weight of the lead. 110 kilonewtons per cubic meters. Okay, so that's the given. So let's solve first letter A. For letter A, our figure is this one. So what are the forces present here? We have the weight of the cylinder container. We have W, which is 3.825 kilonewtons. We have the buoyant force being applied to the cylinder. So that's BF1. And we have the weight of the lead. Okay, so weight of lead. And Of course, if it is submerged, if the lead is submerged on water, so there is also an equivalent buoyant force on that. So let me just write here. We have buoyant force 2. Okay, so this is buoyant force 1. So we have two buoyant forces again. Okay, so solve this. Let's determine first the buoyant forces based on the figure. So because if we're going to take the sum of all the forces along the vertical, upward positive, we have here buoyant force 1 plus buoyant force 2 minus weight of the cylinder, okay, cylinder, and to be subtracted by weight of the lead equals to 0. Okay, so let's compute separately the buoyant forces first. So buoyant force 1 is unit weight of water multiplied by the volume displaced, 9.81 kilonewtons per cubic meter. The volume displaced is this volume. Okay, volume is, we have diameter, so area times height, area of the cylinder, pi times, okay, sorry, this is pi d squared over 4, so 1 squared over 4, that's the area, multiplied by the depth, 1.2 meters. So this is the volume displaced. Okay, the buoyant force 1 is equals to divide by pi d squared over 4. Okay, that's 9.246. 246, that's in kilonewtons. For buoyant force 2, we have unit weight of water again, multiplied by the volume displaced. So for the buoyant force 2, this is the buoyant force acted by the water to the lead. Okay, so it means that 9.81 kilonewtons per cubic meter, it is multiplied by the volume displaced. So it means that the volume displaced here is just the volume of the lead. Since the lead is fully submerged with water, so it means the volume that is needed for the buoyant force is also the volume of total volume of the lead. Okay, so we cannot solve this yet, the buoyant force 2, since the volume of the lead is unknown. So that's it. Okay, for the weight of the lead, okay, for the weight of the lead, since we have a given unit weight of lead, we can also compute that weight of lead. But since we don't have yet the volume of lead, we can write that again as the product of the unit weight of the lead and the volume of it. So we have 110 kilonewtons per cubic meter multiplied by volume of lead. So here's another value for the weight of lead. Okay, so the weight of container, cylindrical container, we have 3.825 kilonewtons. So that's it. We can now solve it by taking the sum again of forces along the vertical. And from this one, we substitute now the computed values. So BF1 is 9.246 kilonewtons. BF2 is 9.81 kilonewtons per cubic meter multiplied by the volume of the lead minus weight of the cylinder. Okay, weight of the cylinder is 3.825 kilonewtons. Then subtracted by uh, the weight of the lead, which is 110 kilonewtons per cubic meter, multiplied by the volume of the lead. So based on the equation, what we can determine first here is the volume of the lead, since that's the variable here. So that's equals to 0. Combining like terms first. Let's combine like terms. We have 9.246 and negative 3.825. So 9.246 minus 3.825, we have 5.421. 421 kilonewtons. And we have terms here with variable V. Let's add them. 9.81 subtracted by 110. Okay, that's negative 100.19 kilonewtons per cubic meter multiplied by 1 equals to 0. So I'll take this term here on the right hand side of the equation. We have negative 100.19 kilonewtons per cubic meter multiplied by volume of lead equals to negative 5.421 kilonewtons. So divide both sides by negative 100.19 kilonewtons per cubic meter. We can now determine the volume of the lead. Okay, so volume of the lead is equals to 0.0541 cubic meters. Okay, that's the volume. What is required in this problem is how many kilonewtons of lead must be fastened to the bottom. So it means what is required here is the weight of the lead. Okay, so since we already have the volume, okay, using this equation right here, which is the weight of lead, is equals to 110 kilonewtons per cubic meter to be multiplied by the volume of the lead, which is 0.0541 cubic meters. The weight therefore is equals to, okay, so I will just multiply this by 110, 5.952 kilonewtons. So that's the weight of lead required in order for the cylinder to be submerged 1.2 meter below the water surface. If you place the lead or you attach it at the bottom of the cylinder. How about if we put the lead inside the cylinder? Okay, for letter B. So here, for letter B, as you can see here, the lead is inside the cylinder. So it means if we are going again to determine the forces present here, we have the weight of the cylinder, weight of lead, and how about the buoyant force? How many buoyant force will be present here? Okay, So since class, the lead is inside the cylindrical container, it means that the only volume that is being submerged here is the volume for the cylinder, which is that's the only one that is that's the volume that is being displaced, because that's the volume that is occupied by the cylinder. So since lead is inside the cylinder, so we can only consider the volume displaced by the cylinder only. So it means we only have here one buoyant force. Okay, so since lead is not submerged in water, we will not consider the volume of that. Okay, what is only submerged here is the cylinder. Okay, so I hope nakuha natin. Uh, Taking the sum of the forces, we have sum of forces along the vertical equals to 0. This is for letter B. So we have buoyant force is just to be subtracted by weight of cylinder and weight of the lead equals to 0. Okay, so for the buoyant force, I think we can already compute that, because the buoyant force is just the product of the unit weight of water multiplied by the volume displaced. Unit weight of cylinder, that's already given, which is 3.825. So make it in kilonewtons to be consistent. And weight of lead, which is required. Okay, so substituting now, unit weight of water, kilonewtons per cubic meter. Volume displaced, again, the volume displaced is just for the volume for the cylinder. Okay, so the volume displaced by the cylinder, we have pi d squared over 4 multiplied by 1.2 meters. Okay, subtracted by 3.825 minus weight of lead equals to 0. So let's compute first the buoyant force. The buoyant force is 9.81 times pi d squared over 4 times 1.2. 9.246 kilonewtons minus 3.825 plus weight of lead equals to 0. So subtract that, 3.825, we have 5.421 kilonewtons minus the weight of equals to 0, or 5.421 kilonewtons is equals to the weight of lead. Okay, or the weight of lead is equals to 5.421 kilonewtons. So that's the answer. Okay, so that's it. That's how you solve this problem right here. So letter B is easier since the lead is inside the container. But if that lead is attached at the bottom, so there is an additional buoyant force on the lead because it is in contact with the fluid. Okay, so that ends our lecture class in buoyancy. Thank you for watching. God bless.